facilite la réduction de bande.
Non, non, non.
Je passe en mode.
Multiplicité palicité.
Un théorème d'existence.
Sur la continuité des intégrales fibres en géométrie analytique non-Archimédienne.
Merci de cette invitation. Merci à vous d'être là. Merci aux gens en ligne qui écoutent. Donc, je vais. May I speak English? Should I? Please, okay. No, that's okay. I can. I didn't plan to, but I will. Can you show Deutsch? Also, ich kann nicht da. Okay. So this will be mainly a report on joint work with Antoine Ducros, who is an organizer and is too shy to give the talk himself. So, as I said in the abstract, there is a theory of integration of forms on analytic spaces and non-Archimedean that is due to both of us. And we pre-published something in 2012. And then we started rewriting it from scratch because we had better ideas about how to do it. And so it turned from 120 pages to 560 pages. And in the middle of that, new theorems emerged. And this continuity of fiber integrals is a pretext of discussing this theorem and a bit of the framework. Since I decided to mention continuity of fiber integrals, I want to tell you what continuity of fiber integrals is for everybody except both of us. So that comes back from the theorem of Stoll around 1968. And the framework is the following. You take a morphism of complex analytic spaces. And for Stoll, they are reduced. And there is an assumption that Y is normal, and the fibres of F are equidimensional, and with some dimension. And I think I said it would be, well, this is Stoll's notation, that's key. And so the question is now you take omega, a QQ form on Y, on X, sorry. And what you can do is integrate the form on the fibers of the morphism. So you take the map that sends Y to integral of F minus 1 of Y of omega. This is a function from Y to C. So maybe we assume that supports compact support.
So you need to know in this case there is a notion of multiplicity of the fibres. So
No, you know the theory, so but I'm going to let me wait. Yeah, okay. Don't rush the talk, please. So you may wish to integrate the form omega on the fibers and expect that this has a good behavior. And the answer, the behavior is not good if you do that. Because there are examples like already if you take Q equals 0, so you have a morphism with finite fibers. And if you, omega is the same as a function, and integration is the same of sum. And if you take something like that, here you are counting 2 points, and here you're counting only 1 point. So the behavior is bad. So what Stoll, so here you get 2, and here you get 1. So this is not a nice behavior. And so what Stoll said is observed that one can repair this bad behavior by not integrating omega, but integrating omega times some multiplicity. So Stoll defines a multiplicity function.
So here you should assume that x is also of the right dimension, otherwise you would have
And there is no theorem, so I can assume whatever I want.
Okay. Define a multiplicity function maybe.
Well, I think that's okay for the moment.
No, because if x lies only over a part of y, then you would not be able to endow, which is not
Okay,
normal.
maybe.
So it should be generically dominant. Oh, okay.
For the theorem, it's open. So, a multiplicity function, so on x, and function is strictly positive. And the point is to integrate, will be to integrate the multiplicity times the differential. And this is supposed to have good behavior. So well, it's okay. So now, and the theorem of Stoll is that if x is smooth and f is open, then this function is continuous. So there are examples. So the first point first we look at q equals 0 to understand what happens. So here we want to explain that we want this point to have multiplicity 2, for example, and the fact that one needs some smoothness assumption or normality assumption on y is important as well, because you have this example. You take the non-normal nodal curve and you take its normalization. And if you take the constant function 1 and you integrate on the fibres, you will get 1 everywhere, and here you will get 2. And so it won't be continuous. So you need.
No, but this is not a form of support.
Yeah, okay, you put the point at infinity and it has compact support.
Okay.
Okay, so you need some normality assumption on the base, and also it's from the point of view of an algebraic geometer, who is supposed to know its commutative algebra basis, the basic text. The assumption that the morphism F is open is strange. And for us, it won't be open, it will be flat. But what happens here is that the X is smooth in Stoll's paper, and the fibers are equidimensional, so there is something called the miracle flatness theorem that says the morphism is flat. And for us, the assumption will be flat.
Even if the ground space is not cohen-macaulay?
No, you think something on the. It's not because.
Maybe it's not flat, okay.
No, you know it's a kind of universally open.
Something like that.
Anyway,
yeah.
but
so
also the smoothness on X looks a strange assumption because it should be true.
Yeah, exactly.
When you take a form, you embed X in the C and you take a form in the strict, then it should also be true.
Yeah, but that's the statement of Stoll.
Without assuming X is smooth.
Yeah. It complex manifold, right? So.
but later there was a notion of family of cycles by duality, and so this gives you a family of cycles in the sense of duality,
yeah.
And then you can integrate. I think they know it. I mean, I don't
yeah,
know.
probably, but I couldn't find some better reference.
So
that's okay. So probably the theorem should hold with some flatness assumption and.
No, but you shouldn't assume that X is smooth.
No, so the morphism should be anything, and the spaces should be anything, but the morphism should be flat.
For us?
No, for us, it will be that, and in complex geometry, it should be that otherwise.
No, I don't think it should be. It should be for the continuity. It doesn't have to be flat. Just topological thing. It should be.
Yeah, this example.
No. I mean the base is normal.
Okay, but we don't need that the base is normal, for example, and the theorem every state. And last comment I want to make is that what happens in the easiest case when there is no singularities for the morphism, so it means that the morphism is smooth, and then it means that it's a finite covering for relative dimension 0, or smooth, and then the theorem is just the continuity of integrals depending on the parameter, if you pay attention. So the point is to generalize this to more geometric, to geometric frameworks which are more complicated. Okay, so the non-Archimedean analog. So this is due to, so there is a theory. So we will take a, well, the field won't be important, it never happened in the talk, but then let's take a complete non-Archimedean field, complete with respect to the non-Archimedean absolute value. And so the notation, let's keep the same. Let's take a morphism of K analytic spaces. So here in the sense of Bertolini. And with equidimensional fibre. If no assumption. Sorry? Okay. So with equidimensional fibres of dimension, here's the dimension d, but it could be q as well. And we take, so let's say that the morphism is flat, okay? And we take omega, so a real value, so just to form of type dd on X with relatively compact support. So I want to state, in this case, a theorem before I state the definitions. But and unfortunately I read that, but formally it looks the same. So with Antoine, we developed a theory of forms on analytic spaces which looks like differential forms, and we call them differential form of type, and we have two integers, like as in complex geometry. And it was said that there are real values that have nothing to do with the theory of coherent differential forms, so really real objects. And analytic spaces have a topology, and so it means really that the support of this object is compact over the base. And then, in our theory, we can also integrate differential forms of type dd on the space of dimension d. And so we have the function y integrate over and so this is another analytic space. In fact, it lies not over the ground field K, but over the residue field of the point y for the theory of Bertolini. And dimension d. And so there is a theory with Antoine of integrating forms.
So the value is a real,
the
value of the integral.
Yeah.
It's a real number, right?
So this is a real number.
Okay.
And so, and this is a DD differential form with compact support on this. And so in our theory, it has an integral, and I will explain in the talk where this integral comes from. For the moment, I want to let you please take this for granted. And so forms in the theory of Stoll, forms are, it doesn't explain whether there's infinity or continuous, but the integral is continuous. So here we have something, we assume that if omega has something that we call tropically CR coefficients. So they really come from functions of class CR, and R can be 0, 1, infinity. Then U omega is something that we call G locally, so it will be piecewise locally. Of class 0. And tropically of class 0. And for I equals 0, it's tropically of class C0. In particular, it's continuous. So there are many words that I did not.
Antoine,
yeah.
I think one needs F to be boundaryless also.
Yeah, one needs. What was this? So I will explain at the end of the talk where the boundary assumption comes from. So there are a lot of things to explain. So I have to, in fact, you see this G here. I could say, well, I could put a G right away. So I have to explain what forms are. And that will also explain what does it mean that a function is tropically of class infinity. We come before. What is a function? Tropically CR function. And I need to explain what is the integral of the form. And you see, maybe I will give some ideas of the proof. But there is this is a model theoretic seminar, at least partly. So I will say that it builds on two ingredients. If I don't have time, then the names will. So there is first a definability. I should say tropical definability of the integral of this function. And then some work about integrals depending on the parameter.
About usual integrals, you mean?
Yeah, usual integral. So we have to play both parts of the game. So I won't write, but I could say also why we wanted to prove the theorem. So in our work, there is a version of that, but with a much weaker continuity property that was used because we also have a theory of currents on analytic spaces. And what this theorem says is that when you take the differential form omega and you push it down as a current to the ground space, then this is a current defined by a continuous function. So this was a goal. But for that theorem, we didn't need the full for that part. We didn't need the full continuity statement as stated here. And we also wanted to do something else. Is that, so we have a theory of differential form, but also on metrics on line bundles, on curvature forms of those metrics, and so on. And so we can copy the intersection theory done by integrating Chan classes. And we wanted to prove that in a continuous family of spaces, the degrees, even by integrating Chan classes, don't move. So we know that there are integers, by some other reasons, but we wanted to prove that they are constant, locally constant, so we wanted to prove that they move continuously. And the part of the proof that told us that they were integers could be used to understand in families, but it was too complicated. I mean, we had issues from formal geometry that was not clear how to do. We needed models in families and so on, and we were stuck with reducedness assumptions and so on.
Which kind of models you need?
We needed to have good models, good formal models of morphisms in a relative case, but to take care about the non-reducedness properties that could happen in our family, and so.
And there is a so-called reduced fibre theorem, and in fact its assumptions were a little bit weaker than we expected, and so.
And it was that the reduced fibre, the generic fibre is reduced, and we have no reducedness assumption anywhere, so that couldn't work. So we didn't. So we had two rules to prove this constancy of integrals of Chan classes, and one was doing analysis, the other was doing formal geometry, and the analysis was easier. Okay, so I don't know how the motivation. So now I want to explain basically this, because I want to make sense to the theorem and to show what kind of ideas appear in what we do. Okay, so I want to go to previous motivation for the work of Antoine and me, is that we also wanted to have a non-Archimedean theory of Archimedean geometry. And in an Archimedean geometry, there is a lot of scheme theory part, and there is also on complex spaces something using Chan classes of line bundles and so on. And we wanted to understand the non-Archimedean aspects by mimicking with the analytic point of view in mind, because. Well. And so first of all, we had to understand, and it was clear at that point, that the naive analytic spaces were not good enough. The rigid analytic spaces were not good enough because they don't have a topology in which you can really do what we wanted. We want to know our spaces to carry measures, since we want currents and so on. But Berkovich's theory was clearly more adapted to everything. So that's why we went to Berkovich's theory. Probably if you can do Berkovich topos on a rigid base, you could mimic that, but that's not. So we had to go to Berkovich spaces. The other point is that if you look at an analytic space of dimension n, and take n equals 1, the curves, and you look at what people do in Archimedean geometry. So first of all, the curves look like graphs. Really, it's truly one-dimensional object, the Berkovich curves, and not two-dimensional. And also, if you look at in Archimedean geometry, there are also graphs. So Archimedean geometry for curves. And you see that the natural operators that appear, they are not of degree 1, but they are of degree 2. Something. They look like Laplacians and not differential. So there is something where we want something to be two-dimensional and not one. And we were saved by a paper by Lagerberg which was published in 2012, I believe, but was appeared in archive probably two years before. And Lagerberg has a similar motivation, has a different motivation. He wanted to understand complex, real analysis of convex function. So on Rn, but by copying methods of complex analysis of purely subharmonic functions on C to the n. And so in some sense he wanted to have his real space seen as something with dimension greater than 2. And he was inspired by a formal analogy of the non-Chambert differential operator. Because in the two series you have two different operators that tells you when a C-infinity function is PSH respectively convex. And so in this case you look at the Hessian, which is the determinant of the matrix of second order differential forms. And here in the, maybe if I put a determinant, and here you have the complex non-Chambert operators, which is the determinant of d2f divided by d zg bar. And here the difference is that here we have twice the same coordinate, and here there are two different coordinates.
This is called a real one, how is it called? Also the non-Chambert?
Non-Chambert as well. Yeah, the analysts know that this is formally similar, but the goal was to do some algebraic theory that makes them similar. And this is what Lagerberg did. And so Lagerberg did something very simple. He said we have to take the usual de Rham complex and make it twice, put it twice at the same time. So we just double, so the idea of Lagerberg is just double the de Rham complex. So a PQ form on an open subset U of Rn is something of the form, so you take one set of coordinates of types dimension of size p and q, and you take some function omega ij, which will be C infinity of u, and you put differential coordinates d prime xi, and you take some another one, and you put double prime. Just make it double.
It's an R2N.
Sorry?
It's an R2N or Rn?
Rn, exactly. It's exactly the same Rn. So I and j are just exactly.
Okay.
So you just, instead of writing this for differential form, you just put two differential objects. That's it. It looks very naive. I mean, it's amazing. But and so technically, you take the tensor product of the two de Rham complex over this, and this will be the C infinity function on you. And so on this object, you can put some differential calculus. For example, d prime f would be, f is a function, d prime f would just be the sum of df divided by dxi, d prime xi, and d double prime. You can do that, and you can also differential d prime omega and d double prime omega using the Leibniz rule. Everything works fine, except that I don't want to write the formula because the exponent of -1 is always confusing. And the only example I want to show is that if you take d prime, d double prime of the function f, you just need to differentiate this, and once again, and you get sum of G to F. And I don't run tensor, but the wedge, because I've used the full stuff at a graded algebra. And so you get this.
So the D prime and D double prime anti-commute or commute? What is it?
Yes.
Anti-commute.
Anti-commute. So there is something like that. And if you take the, in the same way as in the complex numbers, you have d bar f, which will be the sum of d to f. And now I can take the determinant of this permission form, and I get n factorial times this, and here I get n factorial times that. So the algebra is okay to mimic for the moment, the algebra mimics what analysts people want. So pretty cool. I will keep the plan for the moment. Because for the moment, I even don't know what any of these objects are. So we want to transfer this theory to analytic spaces. This is our goal. We have this. It was really our goal. We thought about it when we observed that this was doing what we wanted, with some examples that look like they do. We wanted to transfer. So how can one transfer something on the real numbers to analytic spaces? Just by looking, by taking something that we call moment on an analytic space. This is just a map, let's say f from x to the torus Gm. So this is an n-dimensional torus. Because on Gmn, which is basically, essentially, not exactly, but n distinct non-zero coordinates, we can take the absolute value and take the log. So here we have a map from G and n to the real number R that sends a point x to the family of log of, we take the first coordinate of x and we take its log, and same for. And this map is continuous because of the definition of the topology on Gmn. So we get a natural map. And so every time we have a moment from x to Gmn, we have a map from continuous map from x to n, and we can use this map to pull back at least functions to start with. So we will say that a function, so u from x to r is called tropically smooth or tropically CR if every point x in x, there is an open neighborhood. Well, maybe it could be closed. There is a neighborhood. It's better to have a closed neighborhood. U, well, let's call it U, V of x. We want a moment not on the whole space x, but on V. And the function, let's take it compact. And the function phi from R to R of class CR, such that U of x, U of U is equal to U is phi equals with not exactly F, but this map, which we call the tropicalization of F.
This is V.
Okay? So whenever I give myself such a stuff, and can just pull back a function here, yeah, and if I can take C infinity function there. I say that the function is locally C infinity. But it's not, you see, for continuous function, it's not exactly, all those functions are continuous because by composition, but you might have a continuous function here that does not factor through stuff like that. This is why we say tropically of class CR and not of class CR, because for continuous, it's different. It's a stronger condition to be tropically of continuous. It means that you can, it only depends on finitely non-zero analytic functions, finitely non-zero analytic functions.
And F itself is a morphism of analytic spaces?
This one, yes, of course.
Yeah.
That's what the arrow means.
Yeah.
So if you work in those analytic spaces, which are in the sense of like the IHS vector, so they're like the IHS analytic spaces, so they are obtained by gluing the finger, but the point doesn't need to have a finger.
Exactly, it doesn't need to be good.
So then it's to have good morphism, you need a lot of functions.
Thank you for your question. Thank you for your question.
You
So,
see that there is a partition that...
No, but wait, thank you for your question, and you are trying to say the point I wanted to reach now. Okay. So, on an analytic space, because of the reasons you evoke, there is a topology, which is there, a natural topology, and there is also a G topology, where you take a compact of analytic domains or affinoids or whatever on your space. And you could say that a function has not every point as a neighborhood where there is, but there could be finitely many analytic domains or affinoids that contain your point, and the union is inside. And so there is a notion of G tropically C infinity, or it could be so G tropically CR if it is G locally tropically CR. Which is bizarre for the talk. Antoine will find it bizarre because we define G tropical before defining tropical. Okay? So you could say that, for example, you have two domains and they have a common boundary. Your point here is here, and you have one representation here as a tropically C1 function, and here another one, and they have to glue, but you cannot find a function group. That could happen, and that does happen. So in some sense, those are piecewise CR, and the other are CR. And there are spaces where you don't know you don't know about anything else than piecewise CR because you don't have locally functions, and that's it. But
they are like manifolds with boundary.
Yeah. But in most of our text, so the generality is done in the most possible general way all the times. But when the important theorems appear, when we want to do the Stokes formula and everything, those subtleties disappear because we have to make them disappear. Okay. So for differential forms, we will do exactly the same, but it's a bit more complicated because here we could start from functions, and I cannot yet start from differential forms. So to say what a differential form on S, we have to do a shift theory, and we just in some sense pull back formally. So we can take I don't know what it is, probably a category. So we can take domains and moments, and maybe there is something else to add for a reason which explained here, because it's not exactly the same of having a function on the image of something or a function that extends, but if the stuff is compact, then every continuous function extends. So maybe we have to fix something. And okay, and we take omega, so the form APQ of Rn, and we take basically such objects. So this is the form of PQ, and this will give something which I call alpha star omega on V. And we have an inductive systems, and we take shift theory to define when the pre-shift, and then we take the This is given the sheaf, and we take the associated sheaf.
So you have to know when two such things are equal.
Yeah, okay. But I think so
Yeah, I remember it was discussed in some previous talk, I don't remember.
yeah, but because of I did this talk once or twice, and Antoine did as well. So.
In this seminar or
Yeah, I'm not there, I did it, and well, that's okay. So we have to understand when two stuff are equal, and here it's important to know what the images, well, just erase the stuff, the images of f of f top is. So what is the form of f top of v? And here there is a theorem, which it should be attributed probably to Ducros, but I think I will call it the Berkovich-Ducros theorem. And probably Gelfand, no, not Gelfand, but Einsiedler, Karpanoff, and Lindt did as well. So what is that f top of v? If v is compact, then f top of v is not any subset of R to the n. It's a polyhedral compact subset of R. So it's a very piecewise linear object. And when f over star omega will be 0, so if I have a form, so let's take it like that. So if f upper star is 0, if omega restricted to every cell is 0 for every cell C inside of okay, so that makes sense to restrict my omega to this, and then some differential elements will collapse, and then if this is 0, then this is 0.